Hi everyone, thank you for coming. This is my engineering capstone. I'm Jana, and I conducted this project in a team of 5 undergraduate engineers. We're an interdisciplinary team, and over there you can see our final project. It's a CAD render, and that's our team working on the thing. It's called the Diaphragmatic 9000, and we are doing autonomous sorting, inspecting, orienting, and stacking for Senior Metal Bellows, our company sponsor. So our motivation, Senior Metal Bellows is a metal bellows manufacturer located in Sharon, Mass, and they mass produce bellows that are used for various applications in aerospace and defense. So the parts that we are working with in this project are diaphragms, and these diaphragms are quite small. They're thin, and they're about 0.6 inches in diameter, and they are concave and circular, and they've got a small hole punched out in the middle, which is about 0.2 inches in diameter. And these can get welded at the edges after they are stacked, and then that forms a convolution, which can then go on to form a bellow. So what is a metal bellow? I would imagine a bellow used to ignite a fire, for example, or even an accordion, something that expands or contracts in response to pressure or vacuum. So something like this can be used in various engines. This can be used in aircrafts and underwater propelled vehicles. They are essentially flexible tubes that can be used to transport gases for fuel control engines and other things like pneumatic actuators. And we are using parts for smaller applications. So think of like that actuator over there on the screen. So the design problem. Senior Metal Bellows, as a mass manufacturer, needs a way to sort, orient, inspect, and stack these diaphragms that are coming out of a metal press, and the stamping press is actually creating that small donut hole in the middle of these diaphragms at a rate of 1 part a second, which is quite fast. Right now, in the current process, we're manually inspecting with the use of laborers, like operators, and they're going into these small parts that are ejected in a bin, random orientations, and checking them out by eye. And it's really hard to see because these are small and thin, and they're also fragile and easy to damage. So we wanted a way to automate this process, make it efficient and reliable so it can be repeated and make sure there's no defects. So how do we get all those parts that are ejected randomly onto this nice, neat rod over here? Our objectives were to, of course, sort the parts by the concavity at which they are ejected, which could be either concave up or concave down. We wanted to orient them all to face one direction, inspect both sides, and finally make sure that all the good parts are stacked onto a receiving rod. Our limitations were the usual, which would be the time, tooling, and resources available to our engineering team, but also handling, because these parts are actually 1/1000th of an inch thick and so small. We were, losing a lot of diaphragms in the process of testing, and also damage is very easy to cause. Also, in the plans, we wanted to make use of their vertical space on the shop floor because we didn't want to take up too much lateral space. And that's something important because, of course, we wanted to maximize the tall ceilings in the facility. We also had to travel to the facility. So our solution, first we started with our structure, right? We wanted to give the assembly that we were building some height, so we started with this box frame made of aluminum bars. These are extruded in uniform designs, so there's a lot of adaptability in this structure. We can change the location of like the cross members as seen over there and up here, so we can change where those are located. This gives our assembly height, and there's wheels on the bottom, so that's portable. And of course, we can machine these bars, and we can drill, tap, and cut into them, and attach a bunch of fasteners as needed. This is our part inlet. So starting with the sorter, which functions as it's called, it sorts our parts as soon as they're entering at the top over here. And as you can see in that circle, there is a lip, and this lip actually operates to divert all concave up diaphragms that kind of collide with this lip that's located in a very specific area, and they get diverted down to that bottom channel, and they go down that path. While the other diaphragms that are concave down, they actually don't collide with that lip because that lip is at a height, and they pass through that other channel in blue, they get flipped over with that twisting mechanism, and they exit at the bottom into one channel. And now they're all facing one direction. So that was a previous iteration of our sorter, and this final concept here we've got the same sort of idea, except now we've kind of put the channels closer together, just easier to use. We've also housed our twisting mechanism right there in a rectangular prism for safety of the part and ease of printability. And instead of that lip, you can see there's a thin wall, and this wall operates in the same fashion as our earlier design. So concave down parts are traveling down this wall and staying on that left side and going down the flipping mechanism, while the ones that are concave up fall down that other channel and just go through the way they're already facing. And then they both combine into one channel at the end, and now they're all oriented in the same fashion. And here is a picture of the actual sorter in use in our assembly, and it's going to let both streams out onto that first belt. So you've seen the twister being used. That's what we call this part of our assembly. And this was already in use in our earlier sorter and this one as well. But this is essentially just a simple helix, and its purpose is to flip one diaphragm facing one way to the other direction. And our final print of this was in carbon fiber for surface finish. We don't want to damage the part. It's smoother, and for its durability. And those are images of the male and female diaphragms. So how are the parts getting transported? We are essentially going from the first belt, which is up there, down to the second belt there. And what we're working with is a flipper in between, so that once one part gets inspected on that first belt, it gets turned over and inspected on the second belt. And we see the two stands on top of the belts, which are the cameras. And there's a 7-inch height difference. This is the dual inspection software for defects, and this is looking for edges and faces and checking for flaws. This is actually a rippled part, along with being concave, so it's got a height to it because of those ridges on this part, so those can get easily damaged. And this is an image that shows up in the camera using contrast and other features. Finally, we've got the stacker, and this is the outlet of the parts. So this is a simple chute that actually allows the parts to exit the second belt and leave onto that aperture at the bottom that's circular and lets it nest nicely onto that receiving rod. We actually changed our design from that first thing on the left to the second because this one is more flat and allows the part to fall on without falling through, and there's no extra space in between. For part rejection, when we have a bad part recognized by the cameras, we actually have our solenoids receive a signal from our camera system. So the vision recognizes the part as not good in comparison to an already loaded image of a good part. And now the signal is sent to the air components, and that means the nozzle will blast off the part from the belt and make sure that it does not allow the part to get onto that last rod at the very end. And here is a final CAD rendering. So as you can see for scale, this was shown earlier, but the box frame is a little more accurate to what the actual size is. It's about 4 feet in this length and 2 feet in width. And we built upwards, of course, to keep with our constraints. So this bar on the bottom is 3 feet, but then the wheels add some height, and then also our assembly adds a lot of height, right? Because the sorter is mounted on this 2-foot extrusion, and that allows the part to start very tall and end at a lower height and use gravity all across the assembly. Here are some final photos of what we built. There's some really nice 3D prints on the tabletop in different colors. Just nice to be able to distinguish between the two belts. We can show some more angles right here. And then we've got the higher conveyor on the pink light shell that's like actually preventing light from entering the belts so that the cameras are easily able to detect, surface flaws. And in any light setting or under any conditions, daytime, nighttime, interior lighting differences. Here are the belts again. There's our sorter. A few more angles. We've got the electronics underneath and all the wiring kind of set up as a way to secure them from outside passerby. Thank you.
I was wondering if you could speak a little more on the vision model part of the situation. like what framework you're using, kind of if it's out of the box, if you guys designed it yourselves? I'm just curious.
Yeah, so this is actually a software provided to us by the company. They had an in-house vision system by Keystone, which is the company that produces the cameras, the lenses, and the lighting equipment, and also the software. So this is a controller and camera system that is, pre-set up for us. We did have to program it ourselves to recognize the flaws for this particular part, but the software existed already, and it was provided.
Neat.
Thank you.
I'm wondering what you found to be the most challenging part of this, and then also the most rewarding on the flip side.
Of course. So with any design problem, there's always going to be a lot of iterations and design changes along the process. We had to make a lot of design changes to the sorter just for printability and just ways to make it more smooth, because of course gravity, while it is a constant, it kind of depends on angle and some other affecting factors, I guess, even like the shaking or vibrating of the assembly. So we did have to redo a lot of our designs, but I think the most rewarding part was just seeing the dry run work. So we've got the part moving from the sorter down the first belt, flip over, go onto the second belt, and get stacked successfully. And so that's been really nice to see. And it can be used in mass production and really save the company a lot of manual labor. So that's cool.
This is really great, Jana. So do you have like any metrics for your success? Like how fast are the parts moving through, and like what is there like a lower rate of breakage?
Yeah, of course. I think right now we are trying to get the wet run working with the solenoids and the vision system, so making sure that the signal is timed correctly. We are still testing for metrics, and that will be in our feasibility report and demonstration report. But we do have a way to at least now test the dry run and see how many parts are successfully exiting, and we can count those, of course. So that will be soon to come.
Okay, nice. And then follow-up question. What's like the biggest thing you're going to take with you to industry in terms of, the difference between doing a project in a class setting or a lab setting versus like with a industrial client?
So the difference would be that we really needed responsiveness, and also equipment was of the essence. We needed really powerful tools and just expensive equipment, to be frank. Like, these are professional tools used by the industry, and we had to communicate with a lot of company reps for different programmers as well, like the Yaskawa company that provided us with the controls for motorized belts, right? And like the gearboxes had to be purchased ourselves, or with our research rather. We had to do a lot of research on our own, but also take a lot of suggestions and defer to advice from the actual company.
Okay, that's going to be the end of our question part. Thank you so much, and we're going to go into that.